This video is going to talk about the second derivative test. It's another way that we can find maxes and mins. I'm just going to kind of summarize what is written on this page. Let's pretend that we were looking at something that had a maximum, so maybe an upside down parabola. I know that at the very top right here that the first derivative would have to equal 0 there. And then if we were doing the first derivative test, I'd have to show that the first derivative was maybe positive here and that it was negative over here, showing that it had kind of reached the top of a high point and it started going down. And that's fine, we can still do that. It is a little bit of work to maybe show all of that. And so another way that we can work through this is to say, I know that there's a potential high spot here, or low spot, by looking at the first derivative, by showing that the first derivative equals 0 there. But if you look at any example where there's a max, this is also going to be concave down anytime there's a max. And so once I found that potential x value, I plug that into the second derivative, that x value into the second derivative, and if it shows me that it's a negative value in the second derivative, that tells me that's concave down, therefore I have a maximum. Minimums would work the same way. So right here, I know that if I was looking at the first derivative, I know that potentially the first derivative would equal 0 there, so potentially there's a max or min. I could go through and show using the first derivative that it's decreasing here, increasing there. Or I can just test this one point again with a second derivative, and if I plug that x value into the second derivative and my output is positive, that tells me that it was concave up there, meaning that I had to have a minimum at that point. That is basically what is kind of summed up on this entire slide, but more importantly in the second derivative test. So I need to show that I have a critical point, the first derivative equals 0, and then I need to look for what's going on with the second derivative, what kind of sign it has at that point. If for some reason the second derivative equals 0 there, I can't use this test. I do have to go back and use the first derivative test. That rarely happens though. So one quick example, just use the second derivative test to find any maxes or mins for the function x cubed minus 12x minus 5, and I believe this is using a previous example from earlier in this section of notes. So second derivative test says, first of all, look at the first derivative, so g prime of x g prime would equal 3x squared minus 12. And so from there, I first need to figure out any potential critical points. And so I'd set this equal to 0. Right, set the first derivative equal to 0. And then I'm going to solve for x. So I add 12 to both sides. I get 12 equals 3x squared. I divide by 3, so I get 4 equals x squared. I'm going to take the square root of both sides, and my potential or my critical points are plus or minus 2. That's all review from a previous example. But now I want to know at 2 and negative 2, do I have a max or a min, or maybe neither? And so for this particular test, now we go to the second derivative. So the second derivative would equal 6x. And then I'm going to test those 2 points. So I'm going to find what happens if I plug in a negative 2. If I get a negative 2, that means that I have negative 12 at that point for the second derivative. That tells me it's got to be concave down at that point. And at the other critical point, I get a value of 12. That tells me it has to be concave up at that point. So, because it is concave down right here, I'm going to have a max at negative 2 because it's concave down. It's going to be going like that at that point. And here, because this is positive, it's concave up, I'm going to have a minimum there. So the way I write this out, they're actually, I want to know the point values here, the actual coordinates. So I'm just going to go back to the original function, figure out the y values. So at 2, I have a y value of negative 21, and at negative 2, I have a y value of positive 11. Let's just kind of split some of this up here. just so we kind of remember the steps that we did there. And then in this final spot here, I'm going to write out my final answer kind of nice and neat, how I'd like you to justify your answer. And so we're basically just writing out the second derivative test. We're saying this point has to be a relative max because I know there's the potential to be a max from the first derivative, and through the second derivative I know it's got to be concave down, so I get this kind of shape, and the top of that shape is at the x value of -2. And I'm basically writing the same thing. It's a relative min since it's got the potential to be a min or a max from the first derivative, and now I know that it has to be concave up based on the second derivative. I really like this test because I think it's a lot easier to write this stuff out. You don't have to give all the ranges that you've had to do for the first derivative test or with increasing, decreasing, things like that. But do you have to do it that way? No, but if they actually gave you those directions, they would expect to see this kind of work.